And yes, I will give a short introduction to one of the research fields that I'm involved in. And I'll start out by giving a short introduction to why or how I ended up in chemistry the first way. So first I want to show that I grew up in northern Jutland, so close to Aalborg, which is known for Aalborg Akvavit. And I grew up very close to a place where there is a big cemetery for Vikings at Lilholm Høje. Some of you might know it. Besides Akvavit, Aalborg is also known for being a big releaser of carbon dioxide, because we have this Aalborg Portland. It's a factory shown here, and you can actually see it also here in a horizon. So growing up in Aalborg, or close to Aalborg, I was going to school in Aalborg, but I lived here on the other side of the fjord that goes to the town, so in a part in Vendsyssel, in north of the fjord. I got introduced to chemistry around 90, where I borrowed this book from an uncle in the family, one of my father's uncles. So it's a book from the mid-40s. It was quite appealing to me. So I read this book and I got very interested in chemistry. And I was so lucky that we had space in my house that I could have a laboratory of my own. So this is an early picture from one of the first laboratories I established. In the start, I was interested in inorganic chemistry and various other things. And one of the tasks I had was to try to get gold out of old electronics. It, however, never became a very good business. So I gave up after some time because I think I spent more money on the chemicals that I would ever get out of the gold that I got from electronics. So later on, I also went into making chemicals for the window and door factories. So I produced some reagent that could be put on the end of wood and would make the wood heart dark red, whereas the not part of the heart would remain white. And this could then be scanned, and then you could turn the wood so you had the good part turning outside in the window, and this would then last longer than if you just put it randomly. So with this background from my childhood, I was very sure of what I should do, and I of course wanted to study chemistry. So in '99, I started at Aarhus University, and I did my bachelor project in 2002, where I worked on piperidines together with Michael Bolz. And at that time, I was also lucky enough to get external stay. So I went as a Socrates student, what is equivalent to what is called Erasmus student today, to TU Wien, where I spent a lot of time working with Peter Gärtner, working on asymmetric solid phase organic synthesis. So that was quite interesting and new to me, and I was very happy that I got introduced to these techniques. When I came back again, I obtained a grant for a PhD, so I could start a PhD in 2004. And the PhD was actually within medicinal chemistry, looking at cocaine analogs. And I also had some a project with labeling some compounds. There were some compounds from Lundbeck that should be tritium labeled, and later on we also worked on labeling with iodine 125. So in part of this project, I got introduced to various kind of chemistry, and actually also click chemistry, which was also at that time a very hot topic. I also got involved in some hypervalent iodine chemistry, which is something that I'm still fascinated about, and something I'm taking up now and then. During the stay in Aarhus, or doing the PhD, we were also supposed to have an environmental change, just like today. And we actually talked about that I should go to a group in New Orleans working on some cocaine analogs. But in 2005, Katrina hit New Orleans, and there was a big flood. So it turned out to be not a good idea to go there. So quite late, we decided on that I could go to another group in Chicago working on carbohydrates. So here I joined Professor David Kreitsch at USC Chicago and worked on low temperature NMR and arabinofluorination granulations, and this was more or less my first introduction to carbohydrates. I did a bit before I left Michael's lab, and finished this when I came back working on these super armed glycosyl donors. But I was with this last part of my PhD in carbohydrate chemistry, I got hooked on this, and I decided I wanted to go along this direction, and therefore I chose to join Richard Schmidt at University of Constance, which was a very renowned carbohydrate chemistry group. And I was getting the project to synthesize this huge structure here, which is a glycoconjugate found in gram-positive bacteria. It's a cell wall compound, and it's at that time it was not really known what was the biological role of it. So we wanted to synthesize it, and it's of course a very interesting task to synthesize such a huge compound with that many functional groups. But I was fortunate enough to actually finishing the total synthesis, and we got it published just when I left the lab. At that time, I got an offer at University of Copenhagen, and I started out with working at some of the same kind of structures. So here's again a glycoconjugate from a gram-positive bacteria. This time it's a Clostridium difficile. And together with postdoc Wouter Hogendorf, we managed to synthesize this also very big structure, and also got some biological studies on it. Today, we are still interested in carbohydrate chemistry, and the group is essentially split between two types of projects. So one is carbohydrate chemistry, and the other one is in medicinal chemistry. So in the carbohydrate chemistry part, Niklas, Natasha, Asger, Aminas, Wojciech, me, Amine, Simon, and Oliver are working on different projects, and we're covering glycosylation chemistry that I'll talk more about today, mechanistic studies, conformational control of carbohydrates, method development, protective group chemistry, and also something about biomass based chemicals. The last project here is in close collaboration with a group led by Marco Masciletti in Aalborg University in Esbjerg, and here we're also collaborating with several departments at DTU. In the medicinal chemistry part, Martin, Catalina, Christina, Jonas, and Jesper are working on the male contraceptive project, and this is a project together with medicinal doctor Anders Rehfeldt at Rigshospitalet, and we try to develop a male contraceptive. We're also involved in a project with Alice Alanti from Panum about some cell recognition, where we have synthesized some oligosaccharides some years back. I will now present something about a bit more detail about the chemistry we are doing at the moment, and some of the projects we have finalized during the last years. But first, a short introduction to glycosylation chemistry that have been a project that I've been involved in for more than a decade now. So seemingly a glycosylation reaction is quite simple. We have an electrophile, so that's some kind of glycoside with a leaving group that we are often calling a glycosyl donor. And then we have a nucleophile, it could be another sugar. And essentially these two just have to react together to form the glycoside over here. It turns out that it's a bit more complicated. Often you have to add in some drying agents to keep it the reaction dry to get a reasonable yield. You often also have to add some acid scavengers to pick up the acid formed. And often you also have to add excess of the activator here. The mechanism itself is a bit complicated. It's often described as a SN1 type of reaction where we have a leaving group departure, giving this glycosyl cation that can then be attacked by alcohol from either the top side or the bottom side, giving a mixture of products as shown here. When these are reacting, we get liberated H+, which is then picked up by either the leaving group or by this scavenger. It's however even more complicated than that, because the X-, the counter ion, can also interact, and we can get two other electrophiles formed, the alpha and the beta, shown here. So again, a diastereomeric pair of electrophiles that are in equilibrium with the cation shown on the left. These can also react, and sometimes these can even react in a SN2 type of reaction, giving the inversion of stereochemistry as shown here. So a lot of the chemistry we are doing is trying to push the reactions towards the SN2 side over here, so we have a chance to control the stereochemistry in the reactions. So a short introduction to glycosyl donors, and there are some classics within this, and I guess some of them you know already. So there's what is called a Fischer glycosylation. So that's about the simplest glycosylation one can have, and that's just a simple sugar you treat with acid and a simple alcohol, and then you get the glycosylation going on. This is very good if you want to make methyl or ethyl glycosides, but if you want to put two carbohydrates together, you cannot use Fischer glycosylation. So there was a huge breakthrough when Koenigsegg developed glycosyl bromides, as the one seen down here, for glycosylations, because then you could suddenly make more complex systems. So these kind of glycosyl donors are activated by silver salts or by mercury salts, and has essentially for almost a century been the way one could make glycosylations. Later on in the 70s, thioglycosides were introduced, and these have also been or are still very popular glycosyl donors, and this together with the glycosyl fluorides. Both of them have to be activated with stoichiometric amount of a promoter, which makes it maybe less relevant today, I would say. So today we are more into catalytic reactions, and there are especially one type of glycosyl donor that has been proven to be very successful, and this is acid imidates, and there's a trichloroacid imitate down here that I will also get back to later. There are also some other examples, alkenes, for example, like shown over here. But again, here you see that the leaving group is becoming quite big and a bit more complicated. And then finally, we also have some few examples where fluorides have been used under catalytic conditions. So in the next part of our talk, I will focus on the two types of glycosylations that we have been very interested in during the last years. So it's the trichloroacid imidates and it's the glycosyl fluorides. And we're interested in these because they can be activated using catalysis. When you want to develop glycosylations and develop new methods, there's a lot of mechanistic considerations one should take, because it's actually a quite complex systems. So first of all, there's something to do with the glycosyl donor you're using. How stable is this cation? And this will mean something about where the equilibrium between SN1 and SN2 reaction types are. Then there's also something about the counter ions that are involved. So what kind of ions do you have present? What kind of solvents are you using? So polarity plays a huge role on this edge between SN1 and SN2 type chemistry. So there are also some solvent effects. So solvent can actually participate in the reactions, and these are called the ether and nitrile effects, for example. Sometimes the protective groups are also very important, so they can participate, as shown here, where an acetyl group is participating to the glycosyl cation, making this dioxylanium ion intermediate, which will control the stereochemistry in the reaction. So the nucleophile can only attack from above here, or it can also attack on this center here, giving an autoester. Then there's also some considerations about the kinetic versus thermodynamic control, and this is often referred to as an anomeric effect. So if the glycosylation is in equilibrium, you can push it towards the thermodynamic more stable compound, and that will be the one typically with the axial substituent on the one position. There are also considerations about the conformation and how one can alter this conformation. This can be done by protective groups, and it can also be done with changing the conditions, the solvent, for example. Different conformations, as shown here, of the glycosyl cation will lead to different preferred attack of the nucleophile and therefore one can again shift the selectivity by shifting the equilibrium between these glycosyl cations. These conformations are also very dependent on stereoelectronic effects. So if you change the R groups here, you can also shift this equilibrium. Then of course, temperature is important. Drying agents are important. If you add in molecular sieves and other things, they will have an influence. And then if you think about it, you can come up with many other things as well. We chose to look at trichloride imidates, and we did that because we can control the stereochemistry when synthesizing them. So under base catalysis, we can either get the beta, or the equatorial trichloride imitate as shown here, or we can get the alpha. So by controlling the stereochemistry already at this point, if you could then control the stereochemistry in the glycosylation as well and get inversion of product, then we would be able to make a method that would be easier to work with. We're not the first ones to work on this. Schmidt and co-workers have also had ideas during the years. And there's a tendency to that some of these concepts have been more and more complicated, involving rather complex organocatalysts or gold catalysts. And there are some examples shown here. So essentially, we wanted to see whether we could go a bit back to basic and just focus on a glycosyl donor and how to activate that. And to do so, we decided to look a bit more into the mechanism of activation and what actually happened when you activate the trichloride imitate. And at that time, I was so lucky that I could obtain a visiting professorship in China. So I could join the Institute of Cold Chemistry to do the NMR studies there. And essentially what we did was to have a model system. And then we took this system here as sugar that is not too activated, and we have a non-participating group on the 2 position. And then we used excess of catalyst and essentially tried to see what happened when we studied the NMR of these compounds at low temperature. So the first example here, we used a BF3 etherate, and what we essentially see is that at minus 55 degrees, we have the formation of 2 fluorides, the alpha and the beta fluoride. And we see in the beginning of the reaction, we have mainly the beta, but in time, it's anorizing to give essentially only the alpha. So at minus 15 degrees, we only have the alpha. And this is something that is stable. We can recool it again, and we have a stability of this. So when activating trichloride imidates with BF3, we see some formation of the glycosyl fluorides. We also tried to use another common catalyst for the reaction, is TMS triflate. And what we see here is a very fast transformation of the glycosyl donor into the glycosyl triflate. And this is stable up to around 0 degrees, where it's then decomposing to give the amide. So between minus 5 and 5 degrees, we have a fast decomposition of the triflate, but a very clean reaction. Next, we wanted to take something that was less nucleophilic than the triflate, and we decided to use this bis triple imide. And it behaved very different. So at minus 55 degrees, we only have a slow transformation of the trichloride imidate, and that's what we see here. The NH is slowly disappearing, and first after around half an hour, it's completely gone. And then we see the formation of essentially one compound over time. So we have a clear formation of another compound, but it's not similar to the glycosyl triflate as shown before. So in order to figure out what compound is formed, we looked into diffusion ordered spectroscopy. So that's a technique in NMR where you can essentially separate the compounds after their size and their structure. And what we see here is that by doing that with both proton and fluorine NMR, we can see that the sugar signals here are aligning with the TMS signal. So that means that the TMS from our catalyst up here is attached to the sugar. We also see that the fluorine is also having a similar size because we have a similar diffusion. So from this, we can at least get a good indication that this actually connects to our sugar while the triglyceride imitate is still there. When we heat the reaction to around minus 30 degrees, we see a decomposition to this Friedel-Crafts counter compound, which is also different from the one we saw with using a TMS triflate. To get more information about which compound were formed, we made a calibration curve, and then we could estimate the molecular weights of the different intermediates we had. And we see the one with the TMS bistrophil imide is actually fitting very well the calculated value with the one we obtained from both the fluorine and the proton dosi. So with this, we could write up a suggested mechanism for what happens. So we have the activation, we get the TMS silation of the nitrogen, and over time this equilibrates to give more of the beta out here, and then eventually this will break down. So with this as a background, we could go in a lab and do some glycosylations. And essentially we tried out some different conditions, always working in the same concentration, both with the TMS catalyst and also the Bunstedt catalyst, and we see that they are essentially working the same. Most often we observe that the actual triglyceride imidates, so the one having a triglyceride imidate as X here, are more stereospecific, whereas the beta are less. There are some exceptions, and one of them is an example here where we have a manosyl donor, and we get a very high selectivity towards the alpha compound when we take the beta donor, and we can reverse that when we take the alpha donor, we get the beta monocyte. So this is kind of a proof of concept that we can control the stereochemical outcome just by choosing the donor, and else we use exactly the same conditions. This was proved with a lot of other examples, and I'll just bring a few here. So if we have a 2-acetyl-2-deoxy compound, so this kind of type of sugar, this can be synthesized in good yields and with excellent selectivity. And we can also make glycosides with this type of donor. Now it's with a galactostereochemistry and a bit less reactive, but still works very fine. And also an example here with our model system, glycosylating on a 6OH. So again, very selective reactions, excellent beta selectivities in all these cases. This kind of chemistry has later been developed further in a group, and recently Michael and Thomas from a group developed a synthesis where they used beryllium as a catalyst, and beryllium is a very interesting compound because we can change the R prime groups here, so we can use it more or less substituted, and that will change its reactivity. So essentially it's working by first making a complex with the nucleophile, with the alcohol, which makes the proton here more acidic, so that it can activate the triglyceride imidate, and then we have some kind of transfer, so we get a control of the stereochemistry. So with taking a lot of different glycosyl donors and alcohols, so it showed that the yields are very high, up to essentially quantitative yields, and we also get a very high selectivity. So when we start with the actual compound here, we get the equatorial product over here. It has a very broad scope, so we can use very less reactive glycosyl donors, so donors with a lot of electron withdrawing groups on. They still give the selectivity and high yields. We can use reactive or armed glycosyl donors, and we can also make some very reactive glycosyl donors with like this 2-deoxy glycosyl donor, which is notoriously difficult to control the stereochemistry in, but with this method you actually can get a reasonable selectivity. So this has been shown also to work with the equatorial triglyceride imidates. So here we get often a bit less selectivity, so we are not having the same high degree of selectivity, but we still get high, moderate to high alpha selectivity. So it again is working in a stereospecific manner, and we can tune, again as mentioned before, the reactivity by changing the pyridium catalyst. So now I've shown a lot of examples using triglyceride imidates, and this is still one of the main donors we're using in the group because it's relatively easy to synthesize and it's working very nicely in many of these projects. But we also looked into alternatives and actually inspired by some of the work we did earlier where we saw the formation of glycosyl fluorides when activating the triglyceride imidates. We decided to look a bit more into glycosyl fluorides. So it's known that they can be activated in a catalytic way, but it's only very few examples on that when we started out. And but we saw that when we had a poor acceptor present, we actually formed these as intermediates. So that was why we thought it was interesting to see whether we could actually use them as a glycosyl donor. Using a fluoride as a leaving group is not that common, and essentially that's why it's because it has a very strong bond to carbon, much stronger than the other halogens. This leaving group ability is also poor, so we see the conjugated acids pKa is very different from the ones from the other halides. So essentially the stability is much poorer of the F- compared with any of the other halides. So it's a poor leaving group, and that's also why you won't see anybody choosing a alkylating reagent having a fluoride as a leaving group. You will choose something with a bromide instead, for example, or a iodide. So in order to get a fluoride to work as a glycosyl donor, you need something that can activate it. And this is actually something that have been used for, or came out in the early 80s. So Mukayama introduced glycosyl fluorides as glycosyl donors. And he did that by using an activation system involving both some tin and some silver salts. And in this case, the tin is supposedly taking up some of the fluoride formed and helped it away. But it surprised us that when we looked into these old papers, it was never mentioned actually anything with the HF that was supposedly being formed. And also in the catalytic methods that developed at that time, it was never mentioned what actually happened with this HF that must be formed when you have the fluoride leaving and you have a proton in excess from the nucleophile. So we had the idea that maybe the HF was consumed by the glass vessel, and that actually was driving the reaction. So we would expect that the reaction would be slower if we had a reaction vessel without the ability to take off the HF, something like a plastic vessel, for example. So to test this, we did 2 reactions, one in a glass vessel and one in a Teflon vessel. And to our surprise, it turned out that the one in the Teflon vessel was faster. So clearly our first hypothesis didn't really work out. We also noticed that we got a lot of the hydrolyzed sugar formed in the one in the glass vessel, but not in the plastic vessel. So again, to study this in more detail, we went to NMR and we again took the trip to China. This time Michael joined me, my PhD student, and we did a quite intensive work on this reaction, studying it in glass tubes and these fluorinated plastic tubes for NMR, and we again saw that the reactions are faster in the FEP tubes compared with glass. When we add glass into the FEP tubes, we also see a slower reaction as seen here. We could also see that when we did the reaction in the FEP tubes, we had the HF formed over time. So we start down here and we see gradually more and more HF is accumulating in the reaction. So clearly HF is formed in the reaction. When we do the same experiment in glass, we don't see any HF. It's simply just lacking. No matter if we use tryptophan acid or BF3 etherate, there's no HF, but we have this broad peak here forming that is supposedly from silicon tetrafluoride. So in situ we have silicon tetrafluoride formed and some water. When we then try to add HF as the activator of the system, we, to our surprise, saw that absolutely nothing happened when we had it in a Teflon vessel. There was no reaction. After 72 hours, no transformation. Whereas in glass, we actually saw transformation. So this points at that glass, when reacting with HF, forming this silicon tetrafluoride, this is the actual catalyst. And this is quite interesting because if this is the catalyst, then the reaction could potentially be autocatalytic. And therefore, we looked a bit more into this and tried to see if we could demonstrate this. And we took our simple glycosyl fluoride, and indeed we saw when we had it in a glass container, we had this very classic shape of the curve in demonstrating an autocatalytic reaction. So if nothing happens for a long time until like 4.5 hours, suddenly the reaction sets off and is finished within a few hours and hits a plateau. Whereas the one in a FEP tube, nothing happens at all. So this kind of proved that we have an autocatalytic glycosylation. This is actually the first example of an autocatalytic glycosylation. We've also been interested in looking into more sustainable glycosylations. Now I showed you some glycosyl donors that both either contained a lot of chlorides or fluoride. If one could get away of that, that could be potentially interesting, especially on large-scale synthesis. There's also something with atom economy. How can we improve that so we're not having a lot of mass carrying with us that we're just throwing out after interaction? And we need something that is simple so it can be synthesized on a big scale. And one example of this is a method we developed using glycosyl formates. And glycosyl formates are synthesized very efficiently from, for example, the autoester, just by having the formic acid present in some solvent. We get a high yield of the glycosyl formate. We can also synthesize it in reasonable yields from the reducing sugar itself, just by treating it in formic acid neat, and get the new type of glycosyl donor here. And these type of glycosyl donors are actually also very interesting because they work in a way where we can, by using the right catalyst, we can have a glycoside formation, and the leaving group becomes carbon dioxide and hydrogen gas that will leave the reaction. So we have like a traceless reaction. Only the small amount of catalyst added will stay back, and that can then be removed easily. So this is one example of where we're going with some of that glycosylation chemistry. And you can actually see the reaction is bubbling when you add in the catalyst. So you can kind of follow the reaction. When it stops bubbling, there's no more reaction going on, and you can stop the reaction. We also recently worked on even simpler glycosylations where we don't add a catalyst at all. And again, we have done this using our trichloroacetate imidate donors. When we started out the project, it was actually already known that carboxylic acid and other relatively strong acids could work without any catalyst, so like being their own catalyst. So you take the nucleophile, that will be the acid, activating the trichloroacetate imidate and getting compounds like this. But the examples were only on very simple substrates and with a very narrow scope. So we decided to look a bit more into this. And actually by serendipity, I found in doing my postdoc that these kind of sulfonyl carbamates could work as both a catalyst and give interesting end glycosides like this. So we picked up on this again a few years back and started to see if we could broaden the scope of this. And we did this by using different tosyl carbamates, so also introducing other protective groups like CBZ, TROC, ALOC, and BOC. So we could do modifications at this side as well later on. We also changed the tosyl to nosyl because that's easier to deprotect and also turned out to be a bit more acidic, so therefore also a bit more reactive. And we could also show that we could actually use some more complicated systems. So here we have a tyrosine attached to the reactant. And here we have a sugar attached. So we can actually use it to attach sugars to other biomolecules. And that's kind of the idea with this concept. We have done some mechanistic studies. And we have, for example, used this kind of compound here that can do a competition experiment. We have two nucleophiles, but only one side that is acidic enough to activate the trichloroacetate imidate. And from this, the conclusion is essentially that the reaction giving the end glycoside is concerted. We get inversion of stereochemistry. And that's what is seen here. We get inversion in both cases, starting with either the equatorial or the axial triglycerimidates. When we add in salts or we add in more of the nucleophile, we see a rupture of this. Then we start to get attack of the oxygen as well, because we go through some other intermediates and we break this concertedness that we have just having one-to-one equivalent of the two partners. We can also see we can change it by changing the solvents. So again, we have to push it towards the SN2 type of reactions by using very apolar solvents to get the best results. Right now we are continuing in this, and we have just submitted a paper on how to do this on other amino acids, and we also have an example here doing on asparagine. So you can see we can take many different side chains in amino acids, activate them, and do the glycosylation. And again, there's no additives, no catalyst, anything. It's just the two reaction partners that are mixed together, giving one product. So essentially, no waste, nothing. At the moment, we're working on taking this to the solid phase. And again, with the same concept, having some kind of amino acid side chain, we are activating, and then we add in our sugar. So we get it attached to the peptide, and we get these new glycoconjugates. So it's something we're working on right now in the laboratory. So with this, I would finish the talk by thanking the group, especially the people who are working right now in the group. I mentioned them in the beginning of the talk, doing an excellent work within the various projects. I also like to thank the former students who have been involved in the projects I presented here. Especially Thomas and Michael have done a lot of, they've been involved in several of the projects I have shown. And also the other students here have been involved in the projects. And finally, I'd also like to thank the funding agencies who have been supporting this research during the last years. And I'm very thankful to them to support our research. And finally, I would like to thank you for listening.